Hello students, in my today's session, I will briefly discuss about Coulomb's law and its important aspects. Let us start with Coulomb's law. Here you can see in the figure, two charges are given, Q1 and Q2. The distance from the center of Q1 to the center of Q2 is R. Now coming to the context of the book, consider 2 point charges Q1 and Q2 at rest in vacuum and separated by a distance of R as shown in the figure. Okay, so here these two charges Q1 and Q2 are at rest. That means they are not moving from their respective positions, and also they are in complete vacuum. That means there isn't any other charge very near or far away from them. According to Coulomb, the force on the point charge Q2 exerted by another point charge Q1 is F21 is equal to K Q1 Q2 by R square into R cap 12, where R cap 12 is the unit vector directed from charge Q1 to charge Q2 and K is the proportionality constant. Now here the question is, what does this mean? Coming to its brief. Here these 2 point charges Q1 and Q2 are positive. That means they will repel each other by some force. Coulomb said that the magnitude of this force and the direction of this force. According to him, the magnitude of force acting on Q2 because of Q1 is given by F21 is equal to K Q1 Q2 by R square. And the direction of this force will be from Q1 to Q2 in outward, that is R cap 12. If suppose we are interested to find out the force exerted on Q1 because of Q2, then equation 1.2 will become F12 and that is equal to K Q1 Q2 by R square into R cap 21. Okay, so R cap 21 is a unit vector in the direction from Q2 to Q1. Always keep in mind, when we write F21 we will have R cap 12, then we write F12 we will have R cap 21. Okay, so in brief we can say that force acting on charge Q2 because of charge Q1 is equal to K into magnitude of Q1 into magnitude of Q2 divided by the square of distance between them. Okay, so this is the magnitude of force here, that is electrostatic force. Now coming to the important aspects of Coulomb's law. Okay, so keep in mind that if suppose instead of positive charges, if suppose any one of Q1 or Q2 is negative and other is positive, in that situation there will be a force of attraction work between them and the direction will become opposite from this situation. In that situation, the magnitude of force will always be same, that is K Q1 Q2 by R square. Coming to the important aspects of Coulomb's law, as we see from equation 1.2 that the magnitude of the electrostatic force is directly proportional to the multiplication of the amount of charges Q1 and Q2, and the magnitude of Coulomb force or electrostatic force is inversely proportional to the square of the distance between them. The other aspect of Coulomb law is that the line joining the charged particles will be the direction of the force acting between them. Another aspect, in SI unit, K is equal to 1 by 4 pi epsilon naught and its value is 9 into 10 to the power 9 Newton meter square per Coulomb square. Here, epsilon naught is the permittivity of free space or vacuum and the value of epsilon naught is given by 1 by 4 pi into K, that is 8.85 into 10 to the power minus 12 Coulomb square per Newton per meter square. Keep in mind that here 4 pi means solid angle, as you have studied in class 11 that there are two ways by which we measure the solid angle, that is radian and steradian, and again epsilon naught is permittivity of free space. Permittivity means how much anything can pass from a given region. Okay, next aspect. The magnitude of electrostatic force between two charges, each of 1 coulomb and separated by a distance of 1 meter, is calculated by F is equal to 9 into 10 to the power 9 into 1 by 1 square, that is equal to 9 into 10 to the power 9. What does it mean? It means that if suppose you have two charges, each of magnitude 1 coulomb each, and the distance between them is 1 meter. In that situation, the magnitude of the force is equal to, first substitute the value of k, that is 9 into 10 to the power 9 into 1, that is the value of q1 and q2, 1 coulomb we have seen earlier, and then by a square of the distance, that is 1 meter square, that is equal to 9 into 10 to the power 9 Newton. This value 9 into 10 to the power 9 Newton is very huge in quantity, almost equivalent to weight of 1 million ton. We will be crushed like a tin can on this by this force. Okay, in our day-to-day life we never come across this much huge amount of force. Okay, so the magnitude of the force which become our day-to-day life is always in the order of micro coulomb or nano coulomb, that means from 10 to the power minus 3 to 10 to the power minus 6 coulomb. So this is also an important aspect. Okay, all right, the next number 5th point, the fifth aspect of Coulomb's law. In SI units, Coulomb's law in vacuum takes the form F21 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square into R cap 1 2. Here again, epsilon naught is the permittivity of free space. Suppose the charged particles, okay, like proton, electron, or proton and electron, if they are kept in a medium, suppose in water or iron or in any medium where the permittivity is not epsilon naught, what will happen in that situation? In a medium of permittivity epsilon, the force between 2 point charges is given by F21 is equal to 1 by 4 pi epsilon into Q1 Q2 by R square into R cap 1 2. Just see here, it is given here epsilon, means when the charged particles are kept in a medium. Earlier when it was in vacuum, it was, the formula was with epsilon naught. So keep in mind that thing. Since epsilon is greater than epsilon naught, means the permittivity of the medium is more than that of vacuum, the force between 2 point charges in a medium other than vacuum is always less than that in vacuum. That means this equation F is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square into R cap 1 2 will always be far bigger than this equation. That means if suppose a medium is given, in that situation the magnitude of the force will decrease. We define the relative permittivity for a given medium as epsilon r is equal to epsilon by epsilon naught. Relative permittivity means permittivity of any medium with respect to permittivity of free space. R means relative, so epsilon r is equal to epsilon by epsilon naught. For vacuum or air, always epsilon r is equal to 1, because in that situation epsilon r is equal to epsilon naught by epsilon naught. And for any other medium, epsilon r relative permittivity is greater than 1. So please keep in mind while you will solve the numerical sums. Okay. All right. So coming to the next point, Coulomb's law has same structure as Newton's law of gravitation. Both are inversely proportional to the square of the distance between the particles. That means, according to gravitational force, F is equal to G m1 m2 by R square. That means there F is inversely proportional to the square of the distance between the masses. And here in electrostatic force, F is equal to K Q1 Q2 by R square. Here again F is inversely proportional to the square of the distance between the charged particles. Okay. Okay, the next point is the electrostatic force is directly proportional to the product of the magnitude of 2 point charges. That means F is directly proportional to Q1 into Q2 and gravitational force is directly proportional to the product of two masses, that is F is directly proportional to m1 into m2. Even though there are some difference between gravitational force and electrostatic force. What are they? Let us see one by one. Okay. So let us see the difference between gravitational force and electrostatic force. First point, the gravitational force between two masses is independent of the medium. That means whether the masses are in vacuum or in any medium, the magnitude of the force between them will always be equal. As for example, if 1 kg of two masses are kept in air or inside water, that means in first situation if the masses are in air, that means epsilon naught, and in second situation when the masses are in water, that means epsilon w, the gravitational force between these two masses will always be same. There has nothing to do with the medium where the object is kept, where the masses are kept. But in case of electrostatic force, the electrostatic force depends upon the nature of the medium in which the two charges are kept. Okay, that means if we change the medium, the magnitude of the force between the charges will change. Okay, because the medium works as a hindrance between the charged particles. And also when the medium changes, the value of permittivity changes. The gravitational force between two point masses is same whether two masses are at rest or in motion. That means if suppose we have two masses m1 and m2 and either the objects, the masses are at rest, or if they are moving keeping the distance between them always equal, then the gravitational force between them will be same, the magnitude of force will be same. But if suppose the charges are in motion, in that situation instead of Coulomb's force, we have Lorentz force also. That means there will be addition of Lorentz force. Okay, about this Lorentz force we will study in later sections. Next point, the force on a charge Q1 exerted by point charge Q2 is given by F12 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by r square into r cap 21. Here r cap 21 is the unit vector from Q2 to Q1. Okay, that is, it shows the direction of force from where to where. But we know that r cap 21 is equal to minus of r cap 12. So we can write F21 is equal to minus of F12. Okay. Alright, the next point. Therefore, we see that electrostatic force obeys Newton's third law. In class 11, you have studied about Newton's third law, that action and reaction are equal and opposite. And for Newton's third law, there must be two particles. Okay, the expression for Coulomb force is true only for point charges. When we have object of infinite number of charges, okay, in that situation Coulomb's law will be null and invalid. But the point charge is an ideal concept. We never have point charge. However, we can apply Coulomb's law for two charged objects whose size are very much smaller than the distance between them. In fact, Coulomb discovered his law by considering the charged spheres in the torsion balance as point charges, and the distance between the two charged spheres is much greater than the radii of the spheres. Okay, so even if suppose we have a bigger object, okay, then we can consider those objects as a point charge, keeping in mind that the distance between those charges must be far bigger than their own size and shape. Okay, in that situation we will be able to apply Coulomb's law. Okay. In my next session, I will discuss about superposition principle, its mathematical derivation and some important aspects. As previously I have shared you that in Coulomb's law, if suppose we have a lot of charged particles and we have to find out the total electrostatic force, then Coulomb's law is null and invalid. In that situation, to find out total electrostatic force, we need the help of superposition principle. About this, we will see in the next slide, next class. Till then, take care of your health. Bye bye.